Welcome Year 12s to this video. What I'm going to do in this one is show you the first financial scenario really that we're going to explore using recursion. And that financial scenario is simple interest. Before I get to that though, I'm going to just give you a quick overview of what we mean by linear growth. That is, of course, very much linked to what this whole video is about, which is simple interest. That's an example of linear growth. And you'll notice that on this same page here, we're looking at decay, so linear decay. And all that means is reducing in value rather than increasing in value. So as an introduction, before we get to simple interest, you'll see that we have two sequences here outlined. The first one here starting at 7, and if you have a close look, you'll notice that the values are increasing. And then we've got one over here on the right hand side where the values are decreasing. And there's a question, what do these sequences have in common? Well, if we have a look at this one, as we go from term to term, the recursive rule that we could follow would be to add 5 each time. You can see that that's consistently happening. Whereas with this one, obviously they're going down, and each time they're going down by 6 units. So in terms of what they have in common, you'll see that the two terms that are side by side differ by a certain amount. And that difference there is the same for each pair of terms. So for example, if I take this first pair, their difference is 5. And then if I move that across, the difference between this pair of numbers is 5, etc. Over here, difference here is 6, and the difference here is 6. Now I've put -6 there because of course we're going down each time, so it's effectively taking away 6. In terms of what they have in common, they have the same difference. Between each pair of consecutive terms. So I can take any pair that's side by side or consecutive, and they're going to have that same difference between them. Now these particular sequences, whenever you see you have that same difference, we actually call that a common difference. That's I guess the term that's most often used, and they have a name. They are called arithmetic sequences. And the reason is because of that common difference. So if you come across a sequence and it does show that common difference, you can call it arithmetic. Another way of describing it is that it's linear, and that's the most common term that we're going to come across describing these. They represent linear growth, so if the numbers are going up, we see growth, or if the numbers are going down, like the one we saw on the right before, that's a representation of linear decay. When you graph these, so when you graph those terms for different values of n, so for n being the number of iterations, you will always get a straight line, and hence that's why we call it linear growth or linear decay, because it creates a linear relationship when it is graphed. Here's our first sequence that we had before, the 7, 12, 17, etc. And so if we were to write that in a recurrence relation, we'd have V0 equal to 7, our starting term 7. And to get the next term, you take Vn and you add 5. And so you'll see this bit here, I might just put a little box around it. That bit there is the common difference between our terms, so they're always going to differ by 5. But in terms of, I'll just write, we usually call that D, common difference. In terms of how we're going to use linear growth, we're going to use it to model simple interest, and that little bit that's being added on at the end, that's actually going to represent the interest when we look at simple interest. So I'll just make a little note of that. That bit that's being added is the simple interest. Now I'm just going to graph that particular sequence here. So along the bottom, I'll just move up a little bit, sorry. Along this bottom axis here, the horizontal axis, that's going to be n. And so on the vertical axis here is going to line up with 0. So that's going to represent where we haven't actually added 5 just yet. So I'll just go up maybe in 1. So 1, 2, 3, 4, 5, 6. Maybe that won't work actually. So I'll go up in 2s. 2, 4, 6, 8, 10. 12, 14, 16, 18, 20. 30, okay. That will be fine. On that axis there, I'll put Vn, so that's these numbers here that are going to be graphed. And then we'll go just on the bottom here. 1, 2. So I'll go to n value of 4. Okay, so we're starting off at 7. So 2, 4, 6, 8, so in the middle there. That's my first little point. Then we're up to 12, so here. And then 17. 22, and then 27. Now what you should see is that we are creating a straight line. In other words, if I was to put a straight line on this here, which I'll just do quickly, you'll see that they all line up. Or if I was a bit more accurate with my line, it would be. There we go. It creates a straight line when it's graphed, which I've just shown you. And another important thing to note is that if I just look at that difference between, and I'll use just an arrow, the difference between each dot that I've graphed will be identical. And that difference there in this case is 5. So I'm just going to label it as D. The common difference between them should be represented by that common distance, as you can see, between each consecutive term on that graph. Now I'll leave linear decay for now because we'll talk about that when we look at those scenarios, so flat rate depreciation and unit cost depreciation. We'll just focus on simple interest for now, and this style of graph is what we'll see with simple interest, and in fact this particular recurrence relation as well is what we'll see with simple interest. So over the page now, we might get into looking at simple interest. So since this is the first time that we've talked about anything financial, just wanted to touch on interest. You have done interest in the past, probably back in year 9 or year 10 you would have started looking at it. But basically it's something that can be earned through saving, through an investment. So a lot of you might have, say, a savings account in a bank, and you might notice that each month you're paid a small amount from the bank. Sometimes it's just a few dollars, depending on how much you have in savings. It can be quite substantial the more that you have in your account. It is based on a percentage amount, and this particular one, simple interest, is based on the original amount that you put in, not the current amount that you might have. So not the growing amount, but just the initial, which we call the principal amount. Just a note as well that it may not be what you're earning, it might actually be what you're paying, because whenever you borrow money, what you pay back is not just what you borrowed, but also it's almost like a fee or like a rent for using that money, and we call that interest as well. So it can be earned, but it can also be something you have to pay, unfortunately. So simple interest is just put a little box around this, because this is where it differs from the other type of interest, the compound interest. It's fixed amount, so the amount that you're paying or amount you're earning doesn't change week on week or year on year. It is the same amount, and it's always calculated as a percentage of what was put in, and we call that the principal. If it's not the initial amount that you put in, it's the initial amount that you borrowed. Now, a recurrence relation for simple interest is as follows. The starting amount is that amount that you put in to the account or the amount that you borrowed. Here we call that the principal, the starting amount. To get the next value in the investment or the next value in the loan, say that you owe, you take your original amount, or you take the amount that you have currently, or VN, and you add an amount to it. Now, that amount that's added is always a percentage. This is the amount that's being earned or the amount that's being charged for each time period. Now, often we talk about it in years. So in this case, it would be, say, the amount that you're being charged every year or the amount that you're earning every year. And it's fixed, so it's the same amount. We call that D. Now, to get that amount that's in this box over here, I mentioned before it's a percentage of the principal, and that's all that's written here. Percentage being R over 100. So say it was 5%, that would be 5 over 100. If it was 12%, 12 over 100. And since it's a percentage of, that means we multiply it by that principal, so by that original amount. I'll show you some examples in a moment if you're getting a little confused by all these symbols. Once you see it in use, hopefully you'll see it's not too bad. R is that interest rate, and that will be for whatever time period. Like I said, often it's per year. Here's our first example. We've got $325 invested. So automatically I know if that's the amount invested, that's the principal, that's V0. It's invested for 5 years and it's at 3% per annum meaning per year. So PA we often use as just shorthand for per annum. You're going to see PA a lot, just means per year. So 3%, so that means 3 is our R value. All right, set up a recurrence relation. So it's going to give you the value of the investment, so how much you actually have altogether after n years. So first of all, we need to know how much you're going to be earning on this investment. So in other words, what is our D value? So we need to find this. We need to find the percentage of the principal that we're going to get. We're going to earn 3% of 325 each year. We'll do that on our calculator and we'll get 9.75. So you can see it's not very much. However, you've only got $325 in there, so you can't expect to earn too much interest on only a few $100s. Oops. Since we start off with 325, that's our V0. And we're only earning $9.75 on that each year. So to get the next value in our sequence, we take VN and we add 975 to it. So there's our recurrence relation. In the next question, you'll see that we're going to use that now to find the value at the end of each of the first 3 years. Now, since it says here, use the recurrence relation, I'm taking that as meaning use recursion. So demonstrate using recursion how we get these values year on year. So just like what we looked at in the last video, I'm going to show workings. So to get the next value, I need to take V0 and add 975. So this is 325 plus 975. And we get 334.75. So that's at the end of the first year. Therefore, V1, just add the $sign now. You've got now 334.75. Now the following year, we're going to earn that same amount in interest because with simple interest, you do earn the same amount year upon year. So it's still, even though you've got now $334, your interest is still calculated on the principal. So still 3% of 325. That means that the next year, V2, we'll take V1 and earn that, and you'll earn that same amount, 975. So 334.75 plus the 975. Now we've got 344.50. And finally, so that was at the end of the second year, end of the third year, we're going to take out 344.50. Now normally it's not this slow because normally we can just use our sequence on the calculator. I'm just making sure that if I'm given enough space and if there's sort of a prompt there that says to use recursion, that I'm just demonstrating that. So there's the value of the investment at the end of year 1, year 2, and year 3. Now the next question, how much simple interest was earned in those first 3 years? Well, there's a few ways that you can get this. If you ever want to look at how much interest you've earned altogether, you want to just simply, and I've put that in this note, look at the difference between what you've got and what you invested. So how much is in your account, in other words, right now, compared to how much was in there when you first started. Now, this is assuming you haven't added to the account in any other way. This is assuming that you've only earned money from the interest that was being added. So if we do it this way, we've got whatever we've got at the end, which was V3, take away V0. So that will be 354.25. Take away what we started with, 325. This is not a very good investment. Obviously, you're only at 29.25 in 3 years. But again, the point of this question is just to show you, just to demonstrate really a very basic example of simple interest. In other words, you've actually earned 3 lots of 9.75 since you were earning 9.75 per year. This one here, if the money is invested beyond these 3 years, when will it first exceed 400 and what will its value be? So what we could do here is we could use our calculator. We could set up a sequence. So you could put in 325 and press enter, then plus 9.75, enter, and keep pressing enter until it does first exceed $400. So if you do that now with your calculator, what you'll find, you do have to count unfortunately, but after 8 years, we finally tip over the $400 mark, and then the investment is worth $403. So have a go doing that. Make sure that it does work on your calculator, that you are able to generate those sequences. There is another way that that question can be done, and that's actually by setting up a rule, but we'll get to that later in the video. Second example now, we've got $710 this time, so a bit more worthy of earning a bit more interest, I guess. We've got a better interest rate as well, 6.7%. So if we set up our recurrence relation for this one, let's get our interest firstly. The interest that we're earning is 6.7%, so over 100, times by our initial investment, 710. And we get 47.57. Okay, so we're starting off with 710. So Vn plus 1 equals Vn plus 47.57. So again, we're going to use our recurrence relation to find the value at the end of each of the first 3 years. So I might just speed this up a bit. First of all, we're going to add 47.57 each time. So then we'll take that answer and take that answer. and 852, 71. Okay, so therefore our three values are 750, or I might just say B1, sorry. 757.57. There we go. So just like before, we were using that recurrence relation. Generally, it would actually say use recursion. Because you can use your recurrence relation, I guess, and use your calculator as well. I just want to be clear, though, that since we've got this space here, look out for when you are explicitly told to use recursion, because that's when these workings would be essential. Just on to a different question. Find the amount to which an investment has grown. So amount altogether that you have. Find to which. So to which means altogether how much have you got. The reason I underline that is if it said find the amount by which an investment has grown, that means something different to the amount to which. If you're asking how much it's grown by, that means you're finding how much interest was added over that investment period. Whereas if you're finding what it's grown to, that means how much have you got altogether, including your principal, including the interest that you've earned, basically the value of that account. So we've got some, this is how much was invested 1,020, 12.5%, and it's 2 years worth of interest. So first of all, I want to know how much interest am I earning year on year. So 12.5% of 1,020, so that's going to give me 127.50. And now in my calculator, since I haven't been told to use recursion or to create a recurrence relation or anything like that, I'm basically starting off with 1,020. I'm adding on 127.50. That will give me the next one. And then I'm adding on, because I want after 2 years, that answer plus the 127.50 again, V1 plus 127.50. So if you do that, we get V2 equals, and again, I can just do that straight into my calculator, 1275 if I want to. In other words, what we've actually done, and this is probably a good segue for the next thing that we're going to look at, and that is that really what we've done is added 127.50 twice. So it could have been done like this. 2 lots of 127.50 since we earned that each year, and that's added on to 1,020. So really what we've done there is a bit of a shortcut, and that's where we finish off with simple interest. We look at a way of basically we don't want to have to find or use a sequence every single time we're doing a simple interest question. It's not practical. And so what we can do is create a secondary rule that could be used sometimes with simple interest. We call it a rule for finding the nth term. It's really a shortcut without using recursion. So not using recursion, can we just basically multiply how many years we've got or the time period we've got by the amount of money we're earning each time period. Now this table here sort of explains it. I'll just run through it briefly. If you've got 1,000 invested and you're earning 2% each time, 2% of 1,000 is 20, so you're earning $20 each year, or yes, this one is in years, but each time period. So if you have a look down here, that means $20 is added each year. So we go from 1020 to 1040 to 1060. In other words, you can just, if you want the second year, multiply your number of years, which is 2, by 20. If you want the third year, we can just multiply 3 by 20 because you're earning $20 per year. Now, if you have a look down here, we can simplify that as N times D. So your years or time period multiplied by the interest per year. And that is a much faster way than having to say create a sequence and then press enter, 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 enter. God knows how many times in your calculator. Most of the time, you're actually just going to do this. We call it a rule for finding the nth term, which is why you've got here Vn. So it means for any value of n, hence why it's got nth. For example, if you want after 8 years, we call that the 8th. If you want after 13 years, that would be the 13th. So the nth simply means for any time period. We can create this shortcut and we can get a value much faster than a sequence. You'll notice again, D is a percentage of the principal. That's the same as what we did before. Underneath is the same rule, but it's just got D, that value of D substituted. So it's just a longer, looks like a longer, more convoluted rule, but it's the same as the one above, but with D's substituted in. That means you can just do it in one step rather than finding D and then using this rule. So we have got here a question to try. It is a little bit different, which is good. Value of an investment is after year 2. So the total amount that you've got after 2 years is 3377, and at the end of the 3rd year, it's this amount here, 3530.5. They're asking us here how much simple interest is earned each year, but they haven't told us the interest rate, and they haven't told us the initial amount either. But that's okay, because simple interest, you earn the same amount each year. So we've got after 3 years and we've got after 2 years. So if we just find the difference between these two, we can see how much it's grown in that 1 year period. And it must have grown by that interest amount, since we haven't been told about any other money being invested. And so we can see the difference between it's 153.50. Hence that means that's the amount of money that is being earned year on year. That is our D value. We'll just put equals D. We're now asked what was the principal of this investment. So we need to sort of work backwards here. We know that V2, so end of the 2nd year, was 3377. And what we also know is that we're earning 153.50 each year. So if we go from V2 and we take away D, we'll get to V1. If we take away D again, we're going to get to that original investment value. So in other words, we're doing V2 take away 2 lots of D, or 2 times D. So 2 lots of 53.50. And we get 3,070. Now that if we've established the interest we've got each year, but also what we started with, so V0, we want a value of the investment after 10 years. So I'm not going to bother with a sequence here, because I know that, oops, I just wrote that wrong. I know that I can create a rule for Vn. So a rule for the value of this investment after however many years I want. In other words, I can take 3,070 and add n times 153.50, like so. I want after 10 years, so I want V10, so that means substitute 10 into my rule. So it's going to take our original value, add 10 lots of 103.50. Since we earned that every year for 10 years, we get $4,605. As you can see, that's a lot faster than using a sequence. So unless I'm told to use a recurrence relation or to use recursion, this is the rule that I'm going to be using from now on for simple interest. Last few examples just to have a practice of this. We've got Margaret borrowing $22,000 from the bank, and she's got a simple interest rate of 5.2%. So well, she's going to be charged a fair bit of interest year on year. Let's have a look how much. It's going to be 5.2% of 22,000. 1144. So simple interest, not a great one when you're borrowing money because she will be charged that year on year until it's all paid off. It's just generally calculated at the beginning of a loan. But yeah, it's a pretty decent amount of interest for her to have to pay back on this loan. First of all, we're told to actually write down a recurrence relation here, so we'll do so. She starts off with this loan of 22,000. To get the next value in the sequence, which is what she owes, we have to add 1144 to that 22,000. Now, the second part is a rule for the value of the loan VN. So notice the language that they use here. In the past, some students have had there's been a bit of confusion between these two things. A recurrence relation is very different to a rule for a value. So generally we do use this word rule for what we're referring to here, this shortcut, and it's usually rule for VN. So look for that language, rule for VN, when we're creating the shortcut. So we take V0 and we add N times D, so N times 1144. And we get to use this rule now to find how much she owes after 4 years. So in other words, if she's not going to pay off this loan for 4 years, how much in total really will she have to pay back to the bank? So I'm using this rule above. I want after 4 years, so I'm substituting N is 4. So 4 lots of 1144 is what she's going to pay back, including the 22,000, hence that's why it's added. So 26,500, and $76 is what she'll pay back altogether. So as you can see, over $4,000 worth of interest. Last one now, just something that looks a little bit different. Carol has $3,000 to invest. So she has got a V0 principal of $3,000. Now, she wants to earn $450 in interest. So that's our overall earnings. So in other words, if we take N and multiply it by D, that's what we want to equal 450. And she wants that at a rate of 5%, or she's got a rate of 5% per annum. And we want to know over what term she should invest. So in terms of what we've got here, N times D, really we're trying to find what's that N value. So how many years does she need to invest this money for? Now, can we find D? Can we find the interest per year? We've got 5% here, and we've got that original amount. So we can do this, R percent of V0, since we know R is 5%, and we know original value is 3,000. So 5% of 3,000, we get 150. So each year she's going to earn $150, and she needs to earn $450 in total. So, well, you might be able to notice that she's obviously going to need to do this for 3 years, but I'll show you how we can do this with the rule. Oh, except my tablet has just decided to stop working. Good timing. I might just plug it in again, but if not, I'll have to really slowly write this using the mouse, which is a bit awkward. So what we want to do is set up a rule. So we've got VN equals... she's got $3,000 to invest. Oops, gosh, this is going to be a bit of a problem. So 3,000 plus N times D. So N we don't know, but we know D now. Well, it's going to be crazy. Is 150. And what we want to do is solve for n. Now the thing is, what would we put in here for Vn? Since we know that she wants to earn $450 in interest, and we know too, well, now it's working, we know too that she starts off with $3,000, that means that this value here, the total she has altogether, we want that to be $3,450. So we can set up a rule that we can then solve. Like so. When I solve, what I see is that n must be 3 years. Alternatively, and this is how I did it in my head just before, how I knew it was going to be 3, she's earning $450 altogether. If we divide that by how much per year, we can see that's 3 years worth of earnings. So sometimes it's actually a lot quicker just to set it up like this, like I've done here. But I mean, it really depends on the question. You can set up a rule like so. Sometimes what you find is it might not be an exact number of years, so it might come out as like 2.25 or something like that. So knowing how to set up a rule is really important, and to substitute into it like so. And I guess the other really tricky part, well, not tricky, but the other careful part is here. This is total altogether, so this has to be your V0 plus whatever you're trying to earn. So we knew she was trying to earn $450, and we knew she started off with $3,000. So we had to add those two together to know what Vn needed to be. I'll stop there because we've gone through a few questions now and you're ready to have a go on your own. So I'll set those questions for you and you can have a practice. Please make sure you write down any questions that you have along the way, particularly when you're doing the practice, but maybe some questions that you've had throughout this video, to make sure that we can follow up on those in class.